好，大家好，现在是9点，我们准时开始。Hello everyone, now it's at 9 o'clock. We will start right at 9. 感谢 ChinaVR 组织委员会今天让我们有机会Cronus 来这里给大家分享 Openxr。我们今天请到了3位非常非常重量级的演讲嘉宾。第一位呢是 Brent Insco，他是从英特尔公司来的。那第二位呢，他的名字叫 Ryan Pavlik，他是从Collabora 公司过来。第三位呢，他的名字叫 Lachlan Ford，他从微软公司过来。那我就不花时间来介绍他们，他们自己会介绍自己。今天的流程基本上就是说20分钟，Brent 先介绍一下大致上什么是 Openxr，接下来的1小时，Ryan 会非常仔细的跟大家讲解 Openxr，后面呢是15分钟，Lachlan 他会跟大家介绍为什么 Openxr 对于将来我们在发展这个工业，它是非常有用而且不会过时的。他介绍一些特点。最后呢，Brent 会花5分钟的时间来做一个总结。那今天就是大约这么一个情况。现在我把那个麦克风和视频呢交还给会议的组织者艾欣。Okay, now I turn my microphone and video to the meeting assistant and to Brent.
Welcome to our talk on Openxr, Unifying Reality, Building Portable AR and VR Experiences with Openxr. Your speakers for this session will be myself, Brent Insco from Intel. I am the Openxr Working Group Chair. Ryan Pavlik from Collabora, who is the Openxr Specification Editor, and Lachlan Ford, who is a software engineer with Microsoft. Our session today will be broken up into 4 sections. I will give an introduction to Openxr. Ryan will follow up with a deep dive in how to develop applications using Openxr. Then Lachlan will talk about how to future-proof your applications using Openxr. And then I will come back and talk about how you could get started developing for Openxr and what resources are available. So I'll begin the session with the first talk, and we'll introduce Openxr. I'll talk about what Openxr is, the problems we are trying to solve by developing Openxr, and where we are with the latest developments in Openxr. What is Openxr? Openxr is a royalty-free open standard providing high-performance access to AR and VR platforms and devices. Throughout this talk, we will refer to these platforms that support either AR or VR or both as XR platforms. Openxr handles communication to and from an application and an XR platform or device. An XR platform provides the application information such as the head and hand position, information about the controller or input state such as whether a button has been pressed or released. Also, display configuration and form factor information such as whether there is a single display or multiple displays. The application provides the XR device or platform an image or images to display, audio, also haptic responses such as vibrational response in controllers. So what problems are we trying to solve with Openxr? Consider just a few of the XR platforms available. With the AR and VR markets still relatively small, an application developer will want to target as many platforms as possible. But with each of these platforms potentially providing separate proprietary interfaces, it becomes a daunting challenge to support a wider and wider collection of platforms. Before OpenXR, an application developer would have to program to each platform's proprietary API. This becomes a daunting challenge as you support more platforms, both from a development perspective and a validation and testing perspective. OpenXR enables application developers to program to a single common high-performance API, which then provides support across a number of different AR and VR platforms. In developing OpenXR, we had four main philosophies. We wanted to enable both VR and AR applications. Our standard unifies common VR and AR functionality to streamline software and hardware development for a wide variety of products and platforms. Be future-proof. We wanted to make sure we didn't bake anything into the first version of the specification that we would regret later. So we built our API around a flexible architecture to support rapid innovation in the software and hardware spaces for years to come. We also didn't want to try to predict the future of XR technology. We tend to be very bad at it. So we used forward-looking API design techniques to enable engineers to easily harness new and emerging technologies. We also wanted to unify performance-critical concepts in XR application development. XR is one of the most performance-critical use cases on any system today. Reducing and hiding latency in the system is critical to the success of products and applications, and is a key to good user experiences and keeping users from getting motion sickness. Let's provide some context about OpenXR. OpenXR is a Chronos API. It has been developed by a nonprofit industry consortium, which I will talk about more in a second. Extensions play a key part of the design. We have developed a core set of functionality for OpenXR 1.0, but we also want the ability for companies to be creative and extend the functionality on top of this core set of functionality as we figure out what the next things to include in OpenXR are going forward. And we'll talk about a couple of key extensions we've developed within the last few months. Conforming runtimes receive patent and trademark licensing per the IP framework, which gives them patent protection if they develop OpenXR for their platforms. And OpenXR is also royalty-free. As I mentioned, OpenXR is a Chronos API, so let me introduce Chronos quickly in case you haven't come across us before. Chronos is an open standards organization focused on creating interoperability standards to enable applications to access the power of silicon acceleration in domains such as 3D graphics, virtual and augmented reality, and parallel computation. We are a nonprofit, and all the standards we create are open and royalty-free for the industry to use. We've been working on standards for 20 years and have almost 160 members now. Everyone from the largest companies down to small startups spread around the world. We are open to any company who wishes to join to have a voice and a vote in how Chronos standards evolve. Jumping back to OpenXR, I want to mention that OpenXR is rendering API neutral, meaning that the graphics API support is via extensions and are meant to work similarly across all the different graphics APIs you could use with OpenXR. OpenXR contains everything an application needs to drive XR devices in a system, including device discovery, event processing, sensor tracking, and pose calculations on the input side, and frame display timing and composition, plus haptics control on the output side. OpenXR is used alongside a rendering API such as Vulkan to generate the imagery. OpenXR can be used with any 3D API, but a new generation API such as Vulkan is particularly well suited to create applications with high rendering performance and a low latency that are so vital for creating a compelling XR experience. So I've mentioned two already, but I want to talk about some of the Chronos standards that are most relevant to AR and VR. And these fall into four main groupings. Firstly, the 3D rendering APIs, including Vulkan and WebGL, the OpenXR API standard, which this talk is covering. We have initiatives concerning 3D asset formats, including GLTF and the new 3D Commerce Working Group. And lastly, APIs and languages for parallel computation, including vision processing and inferencing. So this slide shows the overall structure of an OpenXR application. I won't spend too much time on this because Ryan will cover this in great detail in the next presentation, but it shows some of the things that you would do in a typical AR or VR application using OpenXR. So let me jump into the latest developments with OpenXR. So the OpenXR working group was formed in late 2016, early 2017. And over the course of the next couple of years, we began development of the OpenXR specification. And in March of last year, we released a provisional specification at GDC to get developer feedback and community feedback. And having received that feedback, we then went on and released the 1.0 specification for OpenXR in July of last year at SIGGRAPH. Over the course of the last year, there has been a number of developments and forward progress with OpenXR and its availability. And I'll talk about a lot of those in the next few slides. We have released the OpenXR 1.0 adopter program, which enables officially conformant implementations, and I'll talk more about that in a bit. There are now officially conformant OpenXR 1.0 implementations for the Windows mixed reality headsets and HoloLens 2. Also, Oculus has OpenXR 1.0 conformant implementations for the Rift and the Quest, and developers can now submit OpenXR applications to the Oculus store. Valve has released a OpenXR 1.0 developer preview via Steam VR. Monado is developing an open source implementation of 1.0. Vario also has a developer preview of 1.0 for their headsets. We also have the latest from Unreal Engine version 4.2.5 that enables optimized rendering and mixed reality capture via OpenXR. And we also have new extensions for advanced UI features, which I will talk about in just a second. We now have the first wave of conformant OpenXR 1.0 devices. These include the Oculus Rift S, the Oculus Quest, the Microsoft HoloLens 2, and the Windows mixed reality headsets. These devices have passed a suite of conformance tests developed by Chronos to ensure that XR platforms conform to the OpenXR 1.0 specification. This suite of tests is available open source on GitHub for use in developing and prototyping OpenXR runtimes, and implementations. Companies using the Conformance Suite are encouraged to contribute test fixes and enhancements to the suite. In order to publicly state OpenXR support, use the OpenXR logo, and gain the patent protection under the Khronos IP framework, companies developing XR platforms must become OpenXR adopters and submit their Conformance Suite test results to the OpenXR working group. Once an official adopter and the test results are approved, Khronos grants trademark and patent licenses. It is important to note that application developers are free to use the OpenXR API and the logo. To demonstrate OpenXR's flexibility, one only needs to look at the initial set of conformant OpenXR devices. We have both all-in-ones and PC tethered devices covered. We have AR and VR devices covered. We also have devices covering both Android and Windows. As I mentioned earlier, extensibility is a crucial part of OpenXR. We want XR platforms to be able to innovate on top of a core set of functionality and push the boundaries. Over the course of the last several months, 2 new cross-vendor OpenXR extensions have been developed focused on advanced user interface capabilities. These include a hand tracking extension, which was developed by Microsoft, Ultraleap, Oculus, Magic Leap, and a number of other companies. This extension provides the application fully articulated real user hand tracking by tracking 26 unique joints per hand. This extension is currently available already from Microsoft and Ultraleap. The second extension enables eye-gaze interaction capabilities for intuitive interfaces. This extension is also currently available on the HoloLens 2. By utilizing extensions, we can explore different ways to provide applications access to the features of the XR platforms. And as we get more experience, we begin to understand the right way to provide access, and we can integrate that functionality into new versions of the core OpenXR specification. Despite it still being the early days for OpenXR, we are seeing great adoption in the open source community. Blender, the 3D creation suite, has adopted OpenXR in its 2.83 release, using it to deliver native VR scene inspection capabilities. And in the Chromium browser project, Chromium 81 uses OpenXR as its default backend for WebXR support, enabling both the Google Chrome browser and Microsoft Edge to use any OpenXR compatible hardware. We are also starting to see adoption in the game space. Microsoft has announced that Minecraft's new RenderDragon rendering engine is building its desktop VR support using OpenXR. OpenXR has already been integrated into the Chromium browser project. But Khronos is going even further by working and cooperating with the W3C World Wide Web Consortium to bring 3D and XR capabilities into the web stack. All 3D in the browser today uses WebGL, a Khronos standard that defines a JavaScript binding over native 3D APIs, and which is used by popular 3D web engines such as 3JS and Babylon. Now we also have the OpenXR native API exposing XR hardware capabilities. And Khronos is working closely with the WebXR working group at W3C to bring that capability into the browser. So just as native XR applications can use Vulkan and OpenXR together, XR applications in the web can use WebGL and WebXR together with the web APIs reaching down into the Khronos native APIs for acceleration and hardware portability. As well as providing application portability between different HMD devices. OpenXR will also provide portability as AR is deployed on new platform architectures, such as edge servers. One architecture being developed uses 5G to connect a lightweight AR device to send its real-time sensor data to an edge server that processes that sensor data, maybe using inferencing, and generates graphical augmentations that can be much more sophisticated than what could be generated on a battery-powered head-worn device. And these are sent back to that device for display. The OpenXR API can hide these round trips over 5G from the application, enabling the same AR application to run natively on an AR device or an AR device connected to an edge server. So in summary, I covered what OpenXR is, why we developed OpenXR, and the problems we were trying to solve. And I also talked about what the latest developments are with OpenXR over the last few months. OpenXR has widespread industry support. It's a collaborative design integrating a lot of the lessons from the first generation proprietary XR APIs developed across a number of vendor platforms to create a new generation API with cutting edge capabilities and a flexible, extensible, future-proof architecture. I think the reason that OpenXR is gaining such wide industry adoption is that it's a win-win for all involved. Software developers, or ISVs, win because they can write an application once and ship on multiple hardware platforms without reporting, both saving time and money and reaching a much larger audience. XR hardware vendors win if they expose the OpenXR APIs on their platform, as they have access to a much larger library of OpenXR compatible applications. And most importantly, end users win, as they will know that the XR applications that they want to run will be compatible with the system they have purchased, growing confidence and the XR market for everyone. Now is the time to get involved with OpenXR. Khronos has open sourced the conformance test and launched the adopters program, enabling companies developing hardware and platforms to start prototyping OpenXR implementations and testing against the specification. We have officially conformant runtime shipping from Microsoft and Oculus, so application developers have real conformant implementations to build their applications against. Plus, we have an additional set of preview implementations available from Valve, Vario, and an open source implementation from Collabora. We're continuing to push the OpenXR specification forward by developing cross-vendor extensions such as the hand and eye tracking abilities and capabilities for advanced user interface support. And we're starting to see OpenXR being used by key games and open source software such as Minecraft, Blender, Google Chrome, and Microsoft Edge. Thank you. And now I'll turn it over to Ryan for his masterclass on developing for OpenXR. Welcome to our talk on OpenXR, Unifying Reality, Building Portable AR and VR Experiences with OpenXR. Your speakers for this session will be myself, Brent Insko from Intel,
现在把麦克交给 Dennis。
Okay, now we turn to Mr. Ryan Pavlik for his talking. Mr. Ryan, I'll hand the microphone and the video to you.
Hello, and welcome to the OpenXR Masterclass. The plan for this part of the talk today is to spend a few moments introducing myself and then discussing the basic object handle types in OpenXR. At that point, we'll have the background to explore how OpenXR models interaction. Then we'll take a deep dive into OpenXR application structure and API usage. If you have any questions as we go, you can post them in the stream and they'll be forwarded to me. I encourage you to download these slides either now or after the talk at the URL on the screen. The slides include complete speaker notes, and mentions of functions and types are all linked to reference pages and the specification, which can be helpful as a reference. My name is Ryan Pavlik. I've been working in the VR realm since around 2009. I've been involved with the OpenXR working group since the first official meeting in 2017. I was elected specification editor for the working group in 2019. I am a principal software engineer at Collabora, where I work on customer projects in the XR team and contribute to Monado, which is our open source OpenXR runtime. There are a number of important object types in OpenXR, which are represented by handles. These are the main handle types. All handle types except XR instance have a parent handle type. In OpenXR, destroying a parent handle also destroys all handles that come from it. For example, if you destroy a session, that also destroys the associated spaces and swap chains. If you destroy an instance, that destroys all the handles of the types shown here, since they all come from the instance. In addition to handles, there are two additional types known as atoms. They're not objects, and they don't have an explicit lifetime. They're just coded numbers that represent some fixed thing in the runtime. The one you'll work with most often is a path. An XR path is a number that corresponds to a string representing a semantic path. Although these have no explicit lifetime, they only have meaning in the instance they're retrieved from. Do not save or reuse these between runs. An important part of immersive technology is interaction. Before we get into the details of how an OpenXR application is structured, let's take a few minutes to look at how OpenXR models interaction, since it might be a new approach for you. OpenXR focuses on the actions that a user takes in your application, instead of on the buttons and controllers that are used to perform those actions. This is an important part of the hardware independence provided by OpenXR. In OpenXR, an action is a semantic or meaningful bit of interaction. It's something that you do. Grab object and teleport are examples of names for actions. Actions that should be available in a given context or environment are grouped into action sets. For example, you might have an action set called menu, one called gameplay, and one called driving. You can have one or more action sets active at a single time. So you can have additional gameplay. So you can have gameplay and driving both active. You do not need to duplicate actions between action sets or create additional action sets, combining others. There are several types of actions available. Boolean is essentially a button action. It is either on or off. Float actions are things like an analog trigger. Vector 2 are two-dimensional floats, things like a thumbstick or trackpad. Pose is a special kind of action that's a tracked object. Frequently, these represent hands. Finally, haptic actions are an output action allowing you to provide rumble or tactile feedback to the user. Once you've established which logical actions a user of your application will make, you can then customize how they actually perform those actions for the hardware that you're testing. This is done using suggested bindings for interaction profiles. For each controller type that you've tested, look up its interaction profile. These are listed in the specification and cover a number of well-known devices. Additional interaction profiles will be added through extensions. For each device you test with, you submit actions and their suggested bindings for the corresponding interaction profile. The suggested bindings are the logical part of the controller that you'd like to use to drive that action. The specific button, for example. You can suggest multiple bindings per action in a call. For instance, both your left and right hands, and thus your left and right controller, can both cause action grab object to happen. The binding path that you'd like to suggest is a hierarchical string like /user/hand/right/input/select/click. This is on the screen. Here you can see that we are referring to the select button on the right hand controller, and specifically the click operation of that select button. For the last two path levels, there are naming conventions and standardized names that are detailed in the specification. All these paths are listed in the interaction profile definitions in the specification. It's important to only suggest bindings for interaction profiles matching devices that you actually tested. Your application will still be able to run on other runtimes. Those runtimes may automatically map your actions to the controller available. As runtimes continue to advance, you can expect that these rebindings will increase in quality and can be updated independently from your application. They may also provide an interface for the user to customize how the actions are mapped to their controller, and perhaps even share these bindings with other users. Remapping or rebinding can also be done to improve comfort or accessibility to support a wider array of users. This part of the specification design is strongly influenced by the success Valve has found with their similar Steam Input and SteamVR input action, binding, and remapping systems. You will typically set up actions, action sets, and suggest bindings for interaction profiles in a single block of code during the startup process of your application. This model is actually enforced by Openxr. Before you can use actions in your main loop, you need to make a call to attach your action sets to a session. This tells the runtime that you're all done setting up your actions, action sets, and suggested bindings. You're going to use them with this session, and that you're not going to change them anymore. This does make your actions and action sets immutable. You can't modify them after this point, and there's a special error code that you'd get if you tried to do that. If you happen to be writing an editor for a game engine where your users would be likely to want to edit their actions as they make their game, the solution for editing actions is that each time you must tear down the session, the actions, and the action sets, and recreate them in order to modify them. This seems like a pain, but there's an important reason that the action setup is done all up front. The main reason is rebinding. We want the runtime to be able to provide the user with the maximum ability to configure how they're interacting with your application right away. To do this, your application must provide the runtime with the maximum information about its interactions as early as it can. That way, when a user launches your application, if you do not have suggested bindings for the hardware that they have, the runtime can remap the actions automatically, or pop up a UI that lets them map your specified actions to the hardware that they have available. This would happen behind the scenes and goes unnoticed by your application. You just get compatibility. If you were able to add actions and action sets later on during program execution, instead of just upfront, it would then interrupt the flow of your application if rebinding needed to be done a second. Additionally, if a runtime supports sharing bindings between users, you'd be able to compose a binding that supports all actions only if the action setup is done all at once. Otherwise, for example, if there's an action or action set that's only used in the last scene or two of your game, then a community-created rebinding might be incomplete if that scene was not yet reached or was on a path that wasn't followed, making it less useful in general. To make this a bit more concrete, I've gone through the sample Hello XR application that's in the Openxr SDK source and summarized the actions and bindings that are used there. The initialize actions member function is where these get set up if you want to look at the source code on your own later. All these actions are in a single action set because the application is very simple. Additionally, all of these actions are specified for both the left and right hands. This uses the concept of sub-action paths. This lets the user both perform an action with either of two hands, but also let you know which one hand actually did it. It's similar to the SteamVR input concept of restrict to device, in case you're familiar with that. The 4 actions in Hello XR represent a variety of action types. We have grab object, which is a float input, hand pose, which is a pose input, quit session, which is a Boolean input, and vibrate hand, which is a haptic vibration output. After creating that action set and those 4 actions, it's time to suggest bindings. There are a number of calls in HelloXR to suggest bindings. I've picked a few of them for 3 different interaction profiles to illustrate some key points. This first call uses the interaction profile KHR Simple Controller. Unlike most other interaction profiles, this does not correspond to any particular specific piece of hardware. Instead, it's a generic, lowest common denominator sort of device that can be mapped to a wide variety of hardware. There are a few things to notice here. Overall, as you'll see is a pattern, the suggested binding path for the interaction profile, starting with user hand left, will be marked as for the sub-action path of user hand left, and similarly for user hand right. In this application, all actions can be done with either hand, but you would not see this pattern if you had actions that could only be performed by one hand. One point about the simple controller is that its select input is Boolean. It only has on or off. We're binding grab object, which is a float input, to user hand left input select click, which is Boolean. This is fine. The runtime will automatically convert that Boolean value to a float 1 or 0. There are conversion rules that are specified in the specification for these common simple cases. The second example is the Htc Vive Controller. Here you can see we've bound the grab object action to a different path. That's because the Vive controller has an analog trigger rather than a button simply labeled select. This analog trigger, which is a float, is now being suggested as our binding for grab object. The runtime will not need to convert a Boolean to a float. The grab object action will get something that's not just limited to 0 or 1, but might be anywhere in that entire range. The last example of suggested bindings is the Oculus Touch controller. The Oculus Touch controller has a float squeeze input. It can report how hard you are squeezing using a floating point value between 0 and 1. The grab object action will get a value anywhere in that range, just like the analog trigger on a Vive controller. Additionally, only the left controller has a menu button. So in this case, we're only suggesting a binding for the left hand for the quit session action, which uses the menu button. We're not suggesting a binding for user hand right for that action, and that's okay. Now that we've covered interaction, we'll move on to the last segment, the structure of an Openxr application. Here's the outline. We'll go into all of these in more detail. First, you get started by configuring and creating your XR instance. Next, you find out where and how to run. This involves looking up a system ID atom and using the view configuration type enum. Then you set up your interaction in OpenXR. This is done using action sets and actions, as we just discussed. Finally, the last setup step is preparing the immersive experience by creating your session, attaching action sets, creating reference and action spaces, and creating your swap chain. The body of your application consists of advancing the frame loop, responding to input, and handling events. When you create an instance, you first need to choose which extensions you want. Very similar to how Vulkan works. In order to make an OpenXR application, you need at least one extension enabled, and that's a graphics binding extension, to choose which graphics API you will use to render. You can find out which extensions are all available on the system that you're running on by using XR enumerate instance extension properties. However, if you don't have any optional extension usage, only required extensions, you can just proceed to create the instance and ask for the extensions you need. It will either succeed if they are all available, or return an error if one or more is not available. There's also a facility for API layers. Like in Vulkan, these provide a way to hook behavior and change the behavior of functions. These can be configured outside of your application through environment variables or similar to make sure that the loader will automatically load them. However, if your application wants to load some explicitly, you can enumerate which ones are available before you create an instance. Similar to Vulkan, there's an application info struct that you should fill out with your application name and engine name version so that runtimes can identify your application. Finally, XR create instance takes that information and hands you an instance handle, which you will use in the rest of your app. You use XR get system to find out if your desired form factor is available. OpenXR 1.0 natively supports, without extensions, stereo head-mounted displays, as well as handheld mono, magic window style augmented reality. However, not all runtimes will support both of these form factors of devices. Part of the app startup process is asking if there is a system of the form factor you need available. There are a few possible outcomes. The form factor that you asked for might be available, in which case you'll get a system ID. It might never be available if the device that you're using can't do the form factor that you asked for. If you're on a desktop and you ask for Magic Window AR, for example. Or finally, it might be temporarily unavailable if it's perhaps not plugged in, or if it needs to transition to a different mode in order to be used in that way. For example, a smartphone with a slide-in VR headset is a device that can be used in multiple form factors. And the stereo head-mounted display form factor would be unavailable when not in the headset. Once you have a system, you set up your view configuration. This is where mono, stereo, or even more views come in. If you support more than one view configuration, you can use XR enumerate view configurations to find out which ones are supported by the system you've chosen to make your determination of which one to use. No matter which view configuration you use, you will then call XR enumerate view configuration views to get the details of each of the views for your view configuration. Each view configuration has a known number of views. Mono has 1, stereo has 2, the Vario quad view, which is provided by an extension, has 4, and so on. These are well-known values listed in the specification. Once you have an instance, you can get your interactions set up. These are your action sets and actions. We have already discussed most details of action setup. You create an action set with XR create action set. You create all actions, no matter the type, using XR create action. After creating all action sets and actions, you can suggest bindings. Call XR suggest interaction profile bindings once for each controller type, or interaction profile, that you've tested, passing as many action bindings as you like. If you call XR suggest interaction profile bindings more than once for a single interaction profile, only your last successful call will be considered by the runtime. Note that actions and action sets are children of instance, but they can only be used when attached to a session. The next major handle to create is your session. You'll first want to get your graphics binding ready. Depending on which graphics API you use, there will be a Get API Graphics Requirements call that's specified by that extension. You need to call that before calling XR Create Session, or you'll get an error. This provides useful information on how to configure your rendering in order to get the rendered content onto the display. You then create a graphics binding struct. These are also specified by the graphics binding extensions, and they're all chained on via the next pointer on XR session create info. I haven't talked about the next pointer too much, but similar to Vulkan, OpenXR structures contain a type field as well as a void pointer field named next that allows you to add additional structures to the parameters of a call as a chain. This is mostly used for extension functionality, but there are a few cases in the core specification where using the next pointer is required, and this is one of them. In addition to the graphics binding struct, you must also provide your system ID from earlier. This goes in the XR session create info. Once you've called XR create session, you then need to attach your action sets to it by calling XR attach session action sets. As we discussed earlier, this makes your actions, action sets, and suggested bindings immutable. To interact with tracked objects, you use XR space handles. There are multiple ways to get these handles. Several spaces are known as reference spaces. You access these using your XR session and an enum. 3 of these are local space, view space, and stage space. There are additional ones added in extensions. Stage space can be considered a bounded area, standing play environment. Local space is a seated play space. View space is for control and rendering things that are head-locked. To get an XR space from these enums, you use XR create reference space. Another kind of space is an action space. To create these, you use your XR session and a pose action. The result is an XR space, just the same as with create reference space. So your use of them after creation is mostly the same. For both of these types of spaces, session is the parent handle. Additionally, for both of these space types, you can specify an additional fixed transform at handle creation time. XR locate space is the call used to find the transform from one space to another. Note that you never just find the pose, position and orientation, of a space. You always find the pose or location of a space with respect to another space. For example, you don't track just your hand. You track your hand relative to local or stage space. To render your graphics, you will need to create a swap chain. You will obtain your graphics API specific formats through XR enumerate swap chain formats. Then you'll call XR create swap chain one or more times. Once you've created a swap chain, you will access the graphics API specific handles or references to the swap chain images using XR enumerate swap chain images. This is a slightly unusual call. You will pass an array of extension-defined structures to this core OpenXR function. You will want to save the information that comes back from this call to use every frame. The contents of those structures specify, in a graphics API specific way, where to render your image. Within your application's frame loop, there are 3 functions with frame in the name that control the life cycle of a frame. XR wait frame is a scheduling call. When you call it, it blocks and does not return until the runtime determines that you can proceed with head pose dependent simulation and rendering. It also provides you with the predicted display time for the frame you're about to start working on rendering. You'll use this time in all of your calculations and all of your space locations. XR begin frame is executed by your application to mark the start of rendering or GPU usage for that frame. Finally, XR end frame submits the frame for display. It takes a parameter of type XR end frame info, and you populate the XR end frame info display time using the predicted display time from XR wait frame. If your application is using pipelined or multi-threaded rendering, there are some more detailed timing requirements that are important to know. XR begin frame and end frame calls must be ordered as if they were single-threaded, although they may be called from any thread. You can have at most one simultaneous XR wait frame call being executed at a time, and each XR wait frame must be eventually matched with a unique XR begin frame. They come in pairs. Each wait frame has a begin frame, and each begin frame has a wait frame. Additionally, any XR wait frame call will block in the runtime at least until the previous frame's XR begin frame call has been made. Between begin and end frame, once it's time to actually render, you'll need to use the swap chain that you created earlier. XR acquire swap chain image does not give you permission to write to the image, but it does get you the index of the swap chain image you will use this frame. You can use this index to find the graphics API specific handle that you enumerated and cached earlier with your XR enumerate swap chain images call. XR wait swap chain image must be called before writing to that image. It's typically called immediately after acquire. However, as an optimization, you may look up or create your command buffers using just the index from acquire swap chain image before waiting for the compositor to release the image for writing by your application. XR release swap chain image is what you call when you're all done rendering, right before calling XR end frame. XR end frame implicitly uses the most recently released swap chain image for displaying to the device. When you are doing your rendering, you need to render for the predicted display time and for the predicted head pose at that time. The predicted display time comes from wait frame, and XR locate views is how you look up the predicted view pose at that time. It works very similarly to XR locate space. Now that we have an application that can render, we should get input to make it interactive. XR sync actions should be called once per simulation frame in your application. It specifies which action sets should be active for that frame and updates all non-pose input data in those active action sets. Any action sets not specified in the most recent XR sync actions call are considered not active and will not get updated data. After you sync actions, then get the action data. Actions that belong to an inactive action set will return that they are not active. Additionally, actions might become inactive and might not get data if your session is not focused for privacy and security purposes. To get action data from actions, you will use get action state calls. There's one of these calls for each type of action. Pose actions are a little bit different. They continue updating all the time, not just at XR sync actions time, because tracking is latency and time sensitive. To get the data from a pose action, you will usually just create an XR space for it, and then use XR locate space. Only the active-inactive state of a pose action is controlled by XR sync actions. Typically, you'll process most of your input either before you call XR wait frame and begin frame, or after you call XR end frame. There's one other main item that we haven't yet discussed. There is a per instance event queue that contains a range of events. This queue must be polled on a regular basis. Typically, polling once a simulation frame is a good idea. XR poll events requires an instance. However, many events only happen during a session. These events can describe changes to the interaction profile, continuity of reference spaces and tracking, changes in the session state, and other things. You provide an XR event data buffer to XR poll events, and the runtime populates it with an event of some other type. You have to make sure you set the type field to XR type event data buffer before the call. And then when you get it back from XR poll events, check that type value and reinterpret that structure accordingly. Each event type has its own documentation in the specification. Thanks for your time. Hopefully, you found this introduction to OpenXR and exploration of the structure of an OpenXR application to be helpful. I've put a number of resources on this slide that you can follow for additional information. If you have questions that we can't get to during this session, please feel free to drop by one of the community locations for the OpenXR group and leave a note there with your question. I or someone else in the community will be happy to respond.
Thank you, Ryan.
Thanks.
So now we need to switch to Lachlan's speech. Just hold on 1 second.
Hello, ChinaVR. I am Lachlan Ford, and I'm going to be talking about future-proof XR. First of all, before I start, I'd like to thank Brent and Ryan for their wonderful presentations. Brent for taking us through the history and current state of OpenXR, and Ryan for his insightful rundown of the more technical details of the standard. And thank you all for tuning in as well. So what am I going to talk about today? First, I'd like to talk a little bit about myself and my background, and then delve deeper into what I mean by future-proof XR. This talk will be a little more conceptual than the others, but I'll also be diving deep into technical details as well. As mentioned earlier, my name is Lachlan Ford, and I am a software engineer at Microsoft. I work on the mixed reality team, and there I work on HoloLens and Windows Mixed Reality, mainly with a focus in implementation of open standards such as OpenXR and WebXR. And also since early 2018, I've been helping to define and shape the emerging OpenXR spec with the rest of the working group at Kronos. And other than that, I've just been a programmer since forever. So why call it XR? Well, as Brent mentioned, an X looks like a V on top of an A. So it could stand for VR for virtual reality, or AR for augmented reality. But it's more than that. XR is a nascent and emerging technology that is rapidly evolving and transforming. Computing is undergoing a shift towards spatial, and it's impossible to predict what the spatial computing devices of the future will look like. They already take on many forms, from camera pass-through AR on phones and some head-mounted displays, to fully immersive VR and head-mounted stereoscopic AR like HoloLens, as well as projection-mapped cave systems and head-tracked magic window systems. So how do you create a standard that can describe all of that? One which allows the apps that you build now to be compatible with the various forms of XR platforms not only currently available, but also past XR platforms and future XR platforms, as in, how do you achieve backwards compatibility and forwards compatibility? Being able to build a single XR application that is able to target all manner of devices in a backwards and forwards compatible manner is advantageous not only for the consumer, who gets to experience the app on their device of choice, but also developers who can target a much larger audience with far less effort. That was the idea behind many of our design decisions when we created the API. To put it simply, XR is designed to let you build apps that run on many XR systems, leveraging their unique value with the same code. And many of these XR systems do not exist yet. But all this does not come for free. There are some rules that you have to follow to unlock this potential. Now, I'm going to take you through the various parts of the Openxr API and give some background as to why they're designed the way they were, and also examine a few traps that you could fall into when using these APIs. If you avoid these traps, you are more likely to create future-proof Openxr applications. The first I'll talk about is form factor. The form factor is important for informing the runtime what class of XR devices your app supports. Currently there are two values in the core spec, which are head-mounted display and handheld display. This is important as the UX for each is very different, and behaviors of runtime will also be very different. For example, the view reference space is located on the display, which for head-mounted displays implies that it tracks with the user's head. But for handheld devices, it would actually track with the device itself, as the display would be on the device held in the palm of the user's hand. A runtime may support multiple form factors. For instance, a phone may be able to slot into a Google Cardboard-like device and become a VR headset. Apps must be responsive to this and change their UX accordingly. Next, I'll talk about view configurations. Each system has its own ways to render, which is partially encapsulated by the view configuration API. There are general kinds of view configurations, such as mono and stereo, and also special kinds, such as quad vario or Microsoft's secondary mono first-person observer. The special kinds require special handling in code, such as extra application-provided data. You cannot assume that a view configuration will be supported based on the form factor. For example, a head-mounted display does not have to support a stereo view configuration, and a handheld device may support a stereo view configuration. Future platforms may have unexpected kinds of view configurations as well, perhaps due to lens and display technology innovations. Thus, the app has to query the runtime dynamically to handle what view configurations the runtime supports. Next, blend modes. For the best rendering experience, the app should query the blend mode for the runtime and prepare its assets for rendering based on what the runtime supports. For example, you do not want to render black for an additive display, as it will appear transparent. Therefore, if you have a VR app that supports shadows, and you want to port that to an AR system, or have that app support an AR system, you will need to handle the shadows differently if it is on an additive display, such that they don't render transparently. And as with previous examples, you cannot assume that the blend mode matches the form factor. Similar to the view configuration. For example, a VR device that supports pass-through AR will return alpha blend and opaque. Next is the session state lifecycle, which is very important to respect. This allows your XR app to conform to the specific application lifecycle of the underlying operating system correctly. And this prevents any lifecycle issues across platforms by standardizing this at the API level. Next is spaces. It's important to note some reference spaces are optionally supported. For example, the stage reference space is currently not supported on HoloLens. As I mentioned earlier, a very common mistake that I see developers make is using the view space to find the location of the head. This is a mistake, as the view space is not where the head is on all runtimes. For example, in non-head-mounted systems, it will be wherever the screen of the device is. In fact, even on head-mounted systems, the view space origin is somewhere in the region of where the displays are of the system, but it's not in a reliable place on all systems, and so you shouldn't rely on that. Another mistake is using the view space to generate rendering parameters like view matrices and projection matrices. This might appear to work on some runtimes, by virtue of the view space being near where the physical views are, but it will fail catastrophically on other runtimes. The view space is supposed to be used for targeting rays and screen space or view-locked positioning of UI elements. Speaking of generating rendering parameters, the correct way to do it is to always call into the runtime using XR locate views. The runtime will then generate the best rendering parameters which your app should then utilize for rendering. Attempting to generate it yourself is generally a bad idea, unless you are using an extension which lets you augment the data, such as XR Epic View Configuration FOV, which modifies the data in participation with the runtime. Next up is the action system. Now this was designed from the ground up with future-proofing in mind, as XR input devices are constantly evolving and changing. We've seen that just in the last few years, going from simple Vive ones to Windows Mixed Reality controllers to Oculus Touch to the Index Knuckles controllers. There's all manner of shapes and sizes here, and who knows what it's going to be next. Thus, we came up with an abstract verb description system, which describes input at a high level instead of describing it at the input device level, which would be an intractable problem given how much the industry is evolving and how much the device shapes and form factors are changing. Interaction profiles are the runtime's way of describing the class of device that it is using, that it can accept, that is powering the actions that the app has described. It is not a direct description of the current device connected to the system that the user is using. As such, interaction profiles are not devices, and you cannot detect the system or the devices that your app is running on by inspecting the current interaction profile. The purpose of the interaction profile is to inform the UX of the input UX of the app based on the class of input device that is used. If utilized properly, describing your input at a high level using the action system will allow all kinds of future devices to be compatible with your app. It would be pretty amazing if in the future the Openxr apps which we make today would be compatible with crazy future hardware like brain implants and Neuralinks and those sorts of things. Now the last thing I wanted to talk about was extensions. When everything else is covered by the core API, what's left is platform-specific functionality. This functionality is unlocked through extensions. Some are multi-vendor, some are single-vendor. The presence of an extension cannot be assumed, and you must always query the runtime for the extensions that support it before using them. Otherwise, your app will not work on systems that don't support those extensions. And that's all I wanted to talk about today. So in conclusion, Openxr is a platform-agnostic API that attempts to encapsulate as much platform eccentricities and specifics within runtime implementations. The API is general and largely dynamic, but some specific things are required to be handled. Utilizing the API correctly will go a long way towards future-proofing the apps that you build. This will allow apps to support all manner of past, present, and future XR platforms. This has the benefit of not only increasing platform compatibility, but also decreasing maintenance costs by offloading the work of porting to runtime implementers. To get all this, you must play by the rules and not try and outsmart the API. Fingerprinting is generally bad and will cause your app to not be future-proof. You must also never make assumptions about the properties of the system you are running on. Some things that you might get away with on one system will fail catastrophically on another. Anyway, thank you. Thank you for listening.
Thank you, Lachlan. And now we turn the microphone and the video to Brent, and he will make a summary speech.
Okay, thanks, Dennis. So I wanted to come back and talk with you about some of the resources that are available for OpenXR development. And this is mostly for reference. So those of you who are watching can go to the links which I have in the upcoming slides to find some of the resources that are currently available. So as we mentioned, 1.0 is out there, has been out there for a year. So there's lots of information available about what's available. Two of the main landing pages you can go to find out information are the OpenXR landing page at the Chronos site. This contains the specification, reference pages, sample code, and an overview. And you can also go to the link as Ryan had in his presentation that will contain the slides from this presentation today. They may not all be posted yet, but they should all be posted by about this time tomorrow. So what resources are available? So we have the 200+ page OpenXR specification. This includes the specification for a number of extensions, including the ones we've mentioned here, along with probably 15 or 16 other extensions that we have specified. We also have reference man pages for all of the different functions and structures that are contained within the specification. So these have, you can do and find and search much easier and have breakdowns of the functions and the parameters on these man pages. And we also have an overview guide, a 4-page overview which lays out the typical flow for an OpenXR application and groups the various concepts within OpenXR into something that's easily digestible and can serve as a nice quick reference to the overall API. We have a number of locations on GitHub that contain a variety of different information. So our site, OpenXR Docs, contains the source for generating the specification document and reference pages. It also contains the OpenXR header files. We have the OpenXR registry site, which contains the specification, reference pages, and overview guide. We also have a SDK source, which contains source for the loader, some basic API layers, and some test sample code. And we have the current best example code, which is located here as well in an application we have called Hello XR. We also have the SDK, which contains generated files, and this is useful for building the SDK on Windows and Linux, and it's something you can embed in your own projects. We also have the OpenXR-CTS site, which contains the conformance test suite, as I mentioned in my talk earlier. This contains the set of automated and interactive tests which are used to determine the conformance of an XR implementation with the specification. So for those who are developing their own hardware and are prototyping software and want to try and use OpenXR, you can download the conformance test suite and use it to test your implementation as you're building it up. We have a large sampling of additional resources. We have an OpenXR forum and Slack channels as listed at the top. And we are also, despite being the early days and the 1.0 version of the specification, we are starting to get more and more resources available on the web on best practices, how to tune your applications for performance, and basically getting started with OpenXR on a variety of different platforms. So as I mentioned, these slides will be posted on the ChinaVR link that Ryan included and I included. So I encourage you to go check out the links and get more information. With that, I'd like to thank the companies involved in enabling the engineers to dedicate time to OpenXR and getting it developed and out there. And also thanks to all of the engineers that were instrumental in building OpenXR and getting the 1.0 specification out there. So before we go, we'd love to get feedback. We would love to hear from developers and hardware implementers. You know, what have we missed? What could we do differently? What things would help you with your particular situation? So tell us what should be in the specification, what shouldn't be in the specification, and you know how things would need to be changed for your application, your runtime, hardware, platform, OS, etc. You can always give us information through GitHub, as I mentioned, the Slack channel and forums. But we also always encourage those of you out there who want to join Kronos. That's how you can directly influence where the specification goes, and you can help be part of the effort to deliver OpenXR 1.1. And with that, we'll wrap up and say thanks for everyone for attending and listening to our talk on OpenXR.
Thank you so much, Brian and Ryan and Lachlan, for spending your precious evening time to give us excellent talking lecture on OpenXR. Again, thank you so much. Now I'm going to speak some Chinese language. 所以我们大家要非常谢谢Brian、Ryan 和 Lachlan，他们的时间是晚上，已经是9点、10点的那个晚上的时间了，来给我们讲这个。所以呢，我们大家呢，如果接下来的话有什么问题呢，可以直接去参加他们的那个聊天室的讨论。也希望你们能够有兴趣参加Kronos Group 我们的工作小组里面。每个礼拜都有非常多的讨论，这个标准是一版的往前走，所以呢，你们在参与这个讨论之后，就会知道目前他们在做什么，方向是什么，在全球160家公司参与之中的一个标准，非常有意思。Okay, again thank you so much, and let's end the session today. 好，我们今天就结束了，谢谢大家 ，Thank you.
Great, thanks.
Thank you. 谢谢大家，会议到此结束。